Today, we're going to talk about damage and fracture. Previously, in the last lecture, we've talked about the plasticity, which is the rising part of this curve. Eventually, the material would reach the ultimate strength, and after that, it will start to softening. And this corresponds to, in this case, a necking of a metal bar. And if we zoom in, we will see the appearance of voids in this necking region. And if we further load the bar, we will see that these smaller voids would join up to form a larger one, and eventually crack would start to propagate from these edges of the void, and then you have a separation. Today we are going to start with fracture and then move on to damage. This is the topics of today's lecture. We'll start with the Griffith's theory of fracture mechanics, which is the starting point, and then later on I will modify Griffith's theory to include plasticity. Afterwards, we talk about cohesive volume theory, which is the most widely used theory for modeling crack propagations in composites, for debonding, and for matrix cracking as well. Then, based on the cohesive volume theory, people have developed cohesive element, and we will move on. We will then discuss the formulation of a cohesive element there, and then we will talk about smear crack or continuum damage model. So cohesive elements are used along the interface, and then we can use continuum damage or smear crack model to model the effect of damage for bulk materials. Lastly, we will talk about convergence issues with respect to softening behavior. A bit of introduction for why do we need to study fracture damage. We can't simply replace a whole part just because of the occurrence of a single matrix crack or just a small amount of delamination. Then it's important to evaluate how critical these cracks are and to be able to predict how they propagate and when does the structure fail, and also how tough the structure is subject to external impact, and what would be the residual strength after this external impact or other kind of damage. And it is quite expensive to perform a full-scale destructive test to answer these questions. So whenever possible, we should first perform a nonlinear finite element analysis. Here is an interesting video that I found on the internet, which shows the application of nonlinear finite element method on aerospace. You can see the modeling of damage due to impact. Here is the effect of damaged blade, comparison with experiment and simulation. It's a very cool video. So here is a debonding between the stringers and the skin, and the explosive loading type, and this is the drop test simulation. So we do have full-scale actual experiments to simulate the impact on dummies, and also the corresponding simulations. Here it is the bending test to check the limit load, and again a crash simulation and the corresponding test. So it is very important to be able to perform this kind of simulations using nonlinear finite element method, and it is a lot cheaper than performing the full-scale destructive tests. In fracture mechanics, there are three basic modes of fracture: mode 1, 2, and 3. They correspond to opening and then the two shear directions. We have usually different resistance towards the different modes of fracture, and mode 1 is most of the time the easiest to fracture. I think this is also quite easy to understand based on common experience. Peeling mode is always easier than shearing or twisting most of the time. In reality, however, fracture may be subject to a combination of modes. There we need to take into account the mixed mode effect. Fracture mechanics started with the Griffith theory. Griffith basically realized that when we have a fracture, we have a certain amount of energy dissipation. And this energy dissipation is equivalent to the energy required to create the fracture surface. Taken, for instance, this specimen under loading with a pre-crack of length A, before the crack propagates, it has a low displacement curve like this, assuming linear elastic behavior. Up to a certain critical load level, let's say at a displacement of B, the crack starts to propagate. Imagine that it propagates by a little bit, like dA. What would happen if we hold the displacement constant is that now our structure becomes softer, because now we have a longer crack. So the load drops from A to C while we hold the displacement constant. Then there is a certain amount of energy dissipation characterized by the triangle here, OAC. This energy, let's call it du, this is the released energy from the structure due to the propagation of this crack. So this energy must go somewhere, and it went into creating this surface of crack, dA. So if we divide the du by dA, then we get a quantity which is called energy release rate, which denotes the amount of energy release, amount of strain energy release with respect to a certain area of crack propagation. It has a unit of energy per unit area. So, according to Griffith theory, this release of strain energy du contributes to the creation of crack surfaces. So, if we measure the energy required to create the crack surfaces, it should equal to the released strain energy, du. And this energy required to create the crack surface is the so-called fracture toughness. So it has a unit of energy per unit area. So the energy required to create per unit area of crack surface. This theory is valid on brittle materials such as glass. It's actually validated on glass. However, it was not very widely accepted at the time of invention, because it was only valid on glass, and it was proven to be quite far off on metals, so people didn't pay much attention. This is because the theory did not take into account of any plastic deformation. And one of the mathematical consequences of this is that if we look at the stress field around the crack tip, we would then arrive at a stress singularity. This is a little bit non-physical, because no material could withstand an infinite stress level. While based on this theory, these assumptions, there is a rigorous proof that this stress singularity exists. So obviously there must be some additional physical mechanisms there that was not taken into account in this model. Later on, Irwin modified the Griffith's original theory to include plastic deformation around the crack tip. So now, ahead of the crack tip, we no longer have a stress singularity. Instead, we have a so-called plastic zone, where the material is undergoing plastic deformation. So here, the modification is that now the release of strain energy, du, would go into both creation of crack surfaces and the creation of plastic zone. In fact, it turned out that the creation of crack surfaces only consumes a very small amount of energy compared to the creation of plastic zone. So this is the critical reason why Griffith theory was not working on metals, because it would significantly underpredict the energy required to create the crack, because the majority of the energy, which is due to plastic zone, was not taken into account. It is valid for both brittle and ductile materials. So for ductile materials, you have a larger fracture toughness, and brittle materials, you have a relatively much smaller fracture toughness. It accounts for plastic deformation. Yeah, this is basically the main thing about this modification. And because of this plastic deformation, there is no more stress singularity. And then there is a parameter, which is the length of this cohesive zone. It is higher for higher toughness. The tougher the material, then the more difficult it is to fracture it. and it will try to resist fracturing by creating a larger plastic zone before the crack actually happens. So this length of cohesive zone is proportional to this parameter when the crack tip is far away from the boundary. Gc is the fracture toughness. The higher it is, the larger is the plastic zone. Sigma 0 squared divided by E is a measure of strain energy density, and Gc is strain energy per unit area. So strain energy density is a unit. It has a unit of energy per unit volume. So you divide the two, you get the length parameter. In reality, however, this is only valid for regions far away from the boundary, and the actual plastic zone length depend on the geometry. For composites or other so-called quasi-brittle materials, you may not have a complete plastic zone developed. For instance, in this case of double cantilever bending test, you could have all these fibers bridgings between the two crack surfaces. On the right hand, you have a relatively denser network of fibers trying to bridge the two cracks. On the left, you have a much coarser network. So you could imagine having larger resistance towards a separation on the right, and smaller ones or nearly zero ones towards the left. And the beams, they are under quite small deformation. So you, in carbon fiber composites, you don't expect plasticity just because of this bending. So what actually happens is that along this interface, you have a lot of nonlinear mechanisms, and when the crack actually forms, it doesn't, the stress between the crack surface doesn't immediately reduce to zero. Instead, it reduces to zero in a gradual manner with respect to opening. So the larger the opening, the smaller is the stress. So you have a smaller stress towards the left, and the smaller the opening, the larger is the stress. So you here at this crack tip, you retrieve the original stress before any crack propagation. But you see that the stress level now reduces to zero in a rather gradual manner. So here the toughness would include the energy required to create the crack surface and the cohesive zone. The energy dissipation required for the cohesive zone to completely fracture. So it's very similar to the plastic zone modification, except now all the nonlinear events are localized along this interface. We have a similar length parameter, which is the cohesive zone length. It has a similar scaling with respect to these material parameters.